Hi everyone. So today we're going to finish up 6.2. So before we talk about the last thing I want to show you, I do want to do another example with you about the chain rule that we learned. So from yesterday's example, I'm going to go and call this part A. So we can I can ask you to do a second part. How about we find this as a second part? We go try to find dv over dz, and I'm going to ask you to evaluate dv over dz at the point -1, 0, 2. Now, it's important to understand what that means. If you think about dv over dz, notice that z, we identify z as an independent variable, and independent of z go with x and y. So therefore indicate that -1, 0, 2 would be x, y, and z. So keep that in mind. When you're given a number, make sure you understand that what you're plugging in, because I mean, just look at this single one problem. We have R, S, and T, we have X, Y, and Z, we also have U, V. So there are a lot of different variables involved, and you have to make sure you understand wherever a value is given to you, what that value are going to be representing, because you don't want to plug them into the wrong thing. Okay, so now let's go and try to do this, okay? All right, so let's try to do this. So first thing I'm going to do is try to find dv over dz. And I strongly recommend that you pause the video and try to write out the formula yourself first before you see what I'm writing out. Okay, so go for it. Of course, I'm going to continue. So dv over dz would equal to dv over dr over dz plus dv over ds over dz plus dv over dt over dz. Okay. When we did the last example, I didn't have time to write this out, so I'm going to write them out. R is xy, S is yz, and then t is xz. So therefore, the derivative we need will be dr over dz, which is 0, ds over dz, which is y, and then dt over dz, dt over dz, which is in this case x. All right, so those are good. I also need dv over dr, dv over ds, and dv over dt. So what is v? V is, if I look up the function, v is equal to r to the third minus e st. That is an s, okay, right there. Okay, e to st, not e to 5t. So that would be r to the third minus e to the st. Okay, I don't know. Does that look like s? I hope it does. All right, so then what is dv over dr, ds, and dt going to be? Well, let's go for it. Dv over dr would actually equal to 3r squared. But because r is xy, I can say this is 3x squared y squared. dv over ds would equal to negative t e to st. So that would equal to negative xz e to the st, which would be xy z squared. Okay, and dv over dt would equal to negative s e to the st. So therefore would be negative yz e to the xyz squared also. So therefore, dv over dz would equal to dv over dr times dr over dz, but dr over dz is 0, so therefore it's go away. dv over ds, which is negative xz e to the xyz square, multiplied ds dy, which is a y, so therefore become negative xyz e to the xyz square, plus dv over dt, which is negative yz e to xyz, times dt over dz, which is actually equal to x. So therefore become minus xyz e to the xyz square. So that come out to be two of them. So that seems to be what dv over dz is, which is kind of interesting, but that's what it is. Okay, and so now the question comes down to what happened if I evaluate it at negative 1, 0, 2. So if I do evaluate at negative 1, 0, 2, that means would be negative 2 times negative 1 times 0 times 2 e to the negative 1 times 0 times 2 square. Well, because of the 0 right there, this come out to be 0. Alright, so hopefully give you a little bit more example on how this formula work and how do you combine them into a single partial derivative within the larger matrix. The last thing I want to show you is this. It's something called change of variables. We actually go talk about something more about this in chapter 7.4. So this is kind of a little introduction to the concept. So we call, when we're given a function f, that from Rn to Rn, we can call this function a transformations. Because in this case, map from Rn to Rn, therefore basically turning an n-dimensional surface into another n-dimensional surface. Okay, now if this transformation is 1-to-1 and has an inverse, it serves a very unique purpose. If this transformation is 1-to-1 and has an inverse, then it is called a coordinate transformation, because a transformation like this allow us to basically change coordinates within a function. Now, one of the most common expression coordinate transformation that you have already learned is called polar coordinate system, which kind of work out this way. Okay, for example, we go let z equal to f of xy. Okay, and in this scenario right here, x and y would form a rectangular coordinate system. Which is typical of how this works. So therefore, in the plane, the xy plane is our domain, and then the z-axis form our output, the range. But what if we want to change from a rectangular coordinate system into, let's say, the polar coordinate system? Then what we could do is the following. We can define t to be the polar coordinate transformation, where t of r theta would equal to x, y. And we actually know how this coordinate system works. That would be r cosine theta, r sine theta, which is equal to x, y. And now we can change the variable called change of variable, which is what I'm trying to show you. By using a composition. Which is z of equal to f of xy, and change it into z is equal to f of t of r theta. And therefore define z to be a new function, which is the composition between f and t, and more importantly, now the independent variable for z is r theta. So what is the big difference between these two things? This expression right here, z is the dependent variable, and xy are the independent variables. But on the flip side, if I say z equal to f composition t of r theta, now z remain our dependent variable, but now our independent variable are r and theta, effectively changing our coordinate system from xy coordinate system into the polar r theta coordinate system through the composition. Now, one important thing we want to figure out is the following. Well, maybe need is a different word. Maybe we want to. One important thing we want to figure out is how a change of variable affect properties of a function. Some cases you might not think there's a lot of changes going on even though you change the variable, but in some cases it might. One of the most complicated things that that would be an issue is that the fact that when we change the coordinate system, we change how the derivative work, and that have major implication in the sense that it changes the derivative, therefore imply that it changes the differential, and therefore changes the way we integrate. So all this have a ripple effect that start from changing the variable and radiate outward to other things involved. And so one of the things that we want to figure out is what would happen to those stuff. And I think the most likely things that we try to figure out is how does the derivative of the original variable relating to the derivative of the new variable. So what we're going to try to do is the following. In this topic of change of variable, you will be asked to prove some of these relationship between the function derivative with the original variable and with the new variable. So one of the examples will be the following. So let me show you an example to try it out. So here's a very basic example. Let's say we have a transformation. Let t of uv equal to u squared minus v squared 2uv be equal to x and y. And then we go define a function z equal to f of x and y. So what I want to do is the following. If I do change the variable to u and v, okay? If we change the function z to the new variables u and v using z is equal to f of t of uv, show that the following statement is true. Show that if I take the dz over du square plus dz over dv square, that would equal to 4 times u square plus v square multiplied by dz over dx square plus dz over dy square. So I'm going to ask you to show that this statement is a true statement. Now, how do we proceed with something like this? Well, the general idea is exactly the same as how you prove any other things that we have encountered in this class. You are trying to work on either the left side or the right side, or some cases you can work on both to try to get them to arrive into the same expression. And then, therefore, you can use transitive property to say that if the left side equal to this expression, while this expression also equal to the right side, then the left side and the right side are just the same. So how do we do that? This is how we're going to do it. We go start by the following. Notice that z, original variable, is x and y. But now we try to find out what happened if we are changed by u and v. And that presents a composition which then require chain rule to form the derivative. So that's how we're going to deal with this. What I'm going to do is I'm going to do dz over du. According to chain rule, u does not change z directly because z originally is defined for x and y. But u changes x and y, which in turn changes z. So therefore, that's what the chain rule is. And so now I'm going to write out my chain rule. Oh, naturally, maybe I don't have to write it so big. Now that you kind of have an idea as to how that works. So u would actually equal to dz over du actually equal to dz over dx multiplied by dx over du plus dz over dy multiplied by dy over du. Similarly, dz over dv would equal to dz over dx, dx over dv, plus dz over dy, dy over dv. Now notice I'm lining them up. And you should do that too. And I'll explain why that is the case, or you see why as we move along. So now we don't know how z is affected by x or y, because that would be defined by the function f, and we're not given function f. So we don't know that. But we do know how u affect x and y, and how v changes x and y, because we are given those. So let's see. If I know that x is equal to u squared minus v squared, then I would know that dx over du would equal to 2u. And dx over dv would equal to negative 2v. We also know that y is equal to 2uv. So therefore, dy over du would be 2v. And dy over dv would be equal to 2u. That's a v. So therefore, I can now write this out. So dz over dx times dx over du would be the same as 2u dz over dx. And dz over dy multiplied by dy over du, that would be plus 2v dz over dy. Now I'm going to do the second one, same way. Dx over dv is negative 2v dz over dx. plus dy over dv is 2u, so 2u dz over dy. So now what I'm going to try to do is try to construct the left-hand side of our expression, and hopefully somehow it turns to the right-hand side. So how do I do that? I'm going to do the following. I'm going to take the square of these two things. So that just basically means this whole thing square, this whole thing square. That means this whole thing square, and this whole thing square. So nothing to it but square it. So if I square this thing, what do I get? I will have 4u squared dz over dx squared plus 4, or actually 8, uv dz over dx dz over dy plus, okay, maybe I need a little bit of room. Okay, that should be enough. Plus 4v squared dz over dy squared. So it just requires you to multiply it out. So if you multiply it, you should get the same thing I have. Okay. And what happened to the bottom one? Well, same way. So if I do it correctly, that becomes 4v squared dz over dx squared. This is tricky. Is minus 8uv dz over dx dz over dy plus 4u squared dz over dy squared. Now what I'm going to do is the following. What I'm going to do is I'm going to now add them together. And what happened when I add them together? What I have on this side will be dz over du squared plus dz over dv squared equal to. Now, what happened to the right-hand side? Well, let's find out. Oops. So on the right-hand side, I'm trying to add up these two things. And notice that the two middle terms, these two things actually cancel out. And I can combine these two terms which have dc over dx squared together. And when I do that, I should get 4u squared plus 4v squared multiplied by dz over dx squared. Plus, if I add these last two terms together, well, guess what? I also have 4u squared plus 4v squared multiplied by dz over dy squared. Now, just so happens that would imply that they both have a common factor of 4u squared plus 4v squared. So I'm going to factor them out. So that means that would be 4u squared plus 4v squared multiplied by dz over dx squared plus dz over dy squared. And I'm going to further factor of 4 from 4u squared plus 4v squared. And if I'm not mistaken, that is exactly what we try to prove. And that completes our proof. So notice this type of problem very similar to, if I remember correctly, what I asked you to do in chapter 1 about proving some of the properties. But these are definitely obviously more algebra intensive. The way to do this type of question is always start with the partial derivative that you can use the chain rule for. So I mean, don't start with dx over dc over dx and dc over dy, because you cannot use any chain rule. And to do the problem properly, you probably want to identify the composition, so that way you can identify which derivatives require the use of chain rule, and then expand the chain rule and then try to work your way to make it equal to their side. All right, unfortunately, that's all the time I got. And this is the end of 6.2. So that will be the last video. And we're going to continue on 6.3, most likely, I believe, after the next test. All right, so I will talk to you guys again soon. All right, bye-bye.